This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Right now, a machine that has never lived a single day can confidently finish your sentences, pass tough exams, and draft legal memos. Yet, at its core, it's doing one thing: guessing the next word. How does something so simple feel so smart and so strangely human? A 500-page novel, a stack of research papers, and your group chat history walk into a data center. Months later, out comes a model that can draft policy briefs, debug code, and summarize medical studies, despite never understanding any of them the way you do. Something happened in between: training at truly industrial scale. This stage is where LLMs like GPT-4 are forged. Billions of sentences are streamed through a neural network with hundreds of billions of adjustable knobs, and a simple training rule nudges those knobs every time the model's guess is slightly off. Repeat that trillions of times, across thousands of specialized chips running in parallel, and statistical patterns harden into capabilities: fluent writing, translation, even step-by-step reasoning. In this episode, we're going under the hood of that process: the architecture, the training pipeline, and the hidden costs that make these systems possible. Here's the twist we haven't touched yet: none of this power comes for free. Behind every polished answer is a blizzard of matrix multiplications racing across thousands of GPUs, each rented by the minute at premium prices. Scaling laws show that if you pour in more data, bigger models, and more compute, performance rises in a surprisingly smooth way, like steadily adding lanes to a highway and actually getting faster traffic. But this growth has side effects: multi-million-dollar training runs, hefty energy bills, and real environmental footprints that shape who gets to build frontier models. A 176 billion parameter model like Bloom didn't just happen. It was bought, assembled, and tuned into existence. The raw ingredients are oddly concrete: thousands of GPUs, enormous text corpora, and a schedule that looks more like a construction project than a computer program. At the heart of it is a tension. Scaling laws say, if you give me more data, bigger models, and more compute, I'll give you smoother, better performance. Not exponential miracles, just steady, predictable returns. That predictability is powerful. It lets labs budget tens of millions of dollars for a run, roughly estimate the resulting quality, and decide whether it's worth spinning up another wave of GPUs for weeks. But that smooth curve hides messy choices. You can chase raw size, or you can get clever. Mixture of experts models, for example, don't activate every parameter for every token. Instead, they route tokens through a small subset of specialized experts, so each step uses fewer active weights while keeping the total capacity huge. Think of a global consulting firm where each project only taps 2 or 3 niche teams instead of the entire company at once. Data introduces another trade-off. GPT-3's era of scrape nearly everything, Common Crawl, books, Wikipedia, etc., is giving way to more curated, deduplicated, and sometimes privately licensed corpora. Better data can beat brute volume, especially as easy web text runs out and the risk of models training on their own outputs rises. Then there's the physical footprint. Bloom's 433 megawatt-hours and 50 tons of CO2 EQ are a line item you can measure, not a metaphor. Training runs are now constrained not only by money and hardware, but by electricity prices, data center locations, and corporate sustainability targets. These models live at the intersection of machine learning, infrastructure engineering, and energy policy. And after pre-training, the story shifts. RLHF and related alignment techniques reshape this raw capability into something usable by non-experts. Human feedback, preference models, and safety filters become as central to performance as 1 more billion parameters. When you ask a model to write code or analyze a contract, there isn't a single coding chip or legal chip snapping on. Instead, different internal patterns light up depending on the request and the training it has absorbed. RLHF quietly shifts which patterns win. Concretely, if raw pre-training made the model good at both helpful and unhelpful replies, the feedback stage steadily rewards one set and starves the other. Over many iterations, the system becomes biased toward answers that resemble what human reviewers marked as clear, safe, and useful. You can see this in action if you compare a base model to an aligned one on edge cases. The base version might bluntly reveal sensitive instructions or parrot offensive text, while the aligned version hesitates, explains limits, or redirects. Nothing moral has been added. Instead, the probabilities have been sculpted so some regions of its behavior space are much harder to reach than others. Your challenge this week: whenever you get an oddly cautious or carefully framed answer from an AI system, pause and ask yourself, what kind of feedback loop during training might have nudged it to respond this way instead of the raw, unfiltered answer? Then, try slightly rephrasing your prompt, more specific, more neutral, or more constrained, and observe how its behavior shifts. This small experiment will give you a feel for where alignment is helping, where it's overcautious, and how much of what you see is design rather than personality. As context windows grow and models plug into tools, they'll start to feel less like standalone apps and more like control panels for the digital world, typing a request instead of clicking through 10 UIs. That raises awkward questions. Who logs what you ask? Who decides which tools the model may call on your behalf? And how do we negotiate when your local, private assistant disagrees with a cloud model trained on global data and norms? We're still early in learning to steer these systems, a bit like handing a teenager car keys after a few driving lessons. The mechanics mostly work, but norms, laws, and social habits lag behind. As models grow cheaper and more embedded in daily tools, the real frontier becomes not raw power, but how wisely and by whom that power is directed. To go deeper, here are 3 next steps. 1. Open the free Neural Networks Zero to Hero YouTube series by Andrej Karpathy and watch the episode where he builds a tiny GPT from scratch, pausing to compare each step, tokenization, attention, training loop, with how the podcast described it. 2. Spin up a free notebook on Google Colab or Kaggle Notebooks, install transformers from Hugging Face, and load a small model like GPT-2 to actually run .generate with different prompts and sampling settings, temperature, top K, so you can see the next token prediction idea in action. 3. Grab the free online version of The Illustrated Transformer by Jay Alamar, and while reading, sketch, on paper or in a tablet, how tokens move through embeddings, self-attention, feed-forward blocks, logits, annotating it with the exact terms and analogies you heard in the episode, so the mental model really sticks. This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!